Hi, this is Mrs. Villette, and this is a video on quadratic trig equations. Let's understand what we mean by quadratic trig equations first. So quadratic generally means x squared, but we're talking about quadratic with trig, so what we're talking about is seeing a cosine squared or a sine squared. So if you look through all these examples, example 9a, we have a cosine squared. We have a sine, but then also a cosine squared. We have a cosine squared here. So quadratic trig equations just mean that there is a square of the trigonometric function. In order to solve quadratic trig equations, we really need to think about how we would solve if they were just involving x's. So we have some strategies from our previous algebra courses. We have the square root property, factoring in the zero product principle, and the quadratic formula. We're going to focus on these first two because that's usually what will happen with trig equations. So the square root property, let me give you an example with x's. Let's say you had 2x squared plus 1 equals 0. Actually, let's make that a minus 1 so that we're not dealing with complex solutions. So something like that, when there's only a square, so there's no x to the first term, just a square, we would isolate the square. So I'd say 2x squared equals 1, or x squared equals 1/2. And then I would take the plus and minus square root of the right-hand side, and I could keep on going, rationalizing and simplifying and so on. Factoring in the zero product principle is when we have something like x squared subtract 3x subtract 4. Actually, let's make it equal to 4. When we see both an x squared term and an x term, our general strategy is going to be to get everything on one side, 0 on the other. So x squared subtract 3x subtract 4 equals 0. Then we see if we can factor, and I chose this so that it does factor, factors into x subtract 4, x plus 1 equals 0, and then the zero product principle says that the zeros would be 4 and -1. We're thinking about what would make this factor equal to 0, and that would be 4, and then what would make this factor equal to 0, and that would be -1. Okay, so let's see some examples of how to do this with trig equations. Our first example here only has a cosine squared. It does not have a cosine function. So we will start with solving for the cosine squared. That means we will divide both sides by 12. That gives me cosine squared theta equals 9/12, which reduces to 3/4. Since I'm wanting to figure out what the cosine of theta is, I need to apply the square root property. And so that says the cosine of theta is the plus or minus square root of 3/4. In this case, I need to keep on going. And I need to take the square root of the top and the square root of the bottom. So I want to know where is the cosine of theta plus or minus square root of 3/2. Okay, so I know that the cosine is negative root 3 over 2. Actually, let's start with positive. It's positive root 3 over 2 at a 30, 60, 90 triangle, or at pi over 6. So this is the line x equals positive root 3 over 2, which actually intersects the unit circle in two places, and then negative square root of 3 over 2 is over here, which also intersects at two more places. Since there weren't any instructions as to whether I was getting a general solution or a solution in 0 to 2 pi, let's go ahead and just provide the answer in 0 to 2 pi. So in 0 to 2 pi, our answers are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Notice that we got 4 answers because of the plus and minus right here, and that plus and minus is very important so that you get all of the possible solutions. Let's look at example B now. So this is another quadratic. It's squared and cosine, but there is also a cosine term. So I can't use the square root property here. What I need to do instead is treat it, so I want you to think like z squared minus z equals 2. That's quadratic in z, equals 2, not equal 0. And we want to get everything to one side, 0 on the other. So for this problem, that would look like cosine squared of x, subtract cosine of x, subtract 2 equals 0. Now you can either factor thinking about the cosines, or you can factor thinking about the z's. So if I was over here kind of running this parallel problem with z, I'd have z squared, subtract z, subtract 2 equals 0. I'd be thinking about numbers that multiply to -2 but add to -1. So I would do z minus 2 and z plus 1. And just double check that that foils all out, and it does. Similarly, over here I would have cosine of x minus 2 and cosine of x minus 1. Applying the zero product principle, which I abbreviate ZPP, we would get that the cosine of x minus 2 equals 0, or the cosine of x minus 1 equals 0. So cosine of x equals 2, or the cosine of x equals 1. Well, cosine of x cannot equal 2, because the range of cosine is -1 to 1, so that is not going to provide me any solutions. But the cosine of x can equal 1, and the cosine of x is going to equal 1 right here at this line x equals 1, which notice that only intersects the unit circle in one place. Let's go ahead and practice writing both general solutions and particular solutions. So I would just say 0 if I was looking for an answer in 0 to 2 pi, not including the 2 pi. Otherwise, we would say that our general solution would be the set of x, since x was the name of the variable or the angle, such that x equals 0 plus 2 pi k. And you could go ahead and just eliminate that 0, because adding 0 to something doesn't change it, and you could just stick with the 2 pi k part of it. So that would be showing that our solutions are at 0, 2 pi, 4 pi, 6 pi, etc. -2 pi, -4 pi. So just multiples of 2 pi. Okay, for this last problem, we're going to go ahead and change this up because it turned out this example did not work all that well. We are going to change this to cosine squared theta minus cosine squared theta minus sine squared theta plus sine of theta equals 0. So right now this looks like it's quadratic in both cosine and sine. There is also a sine linear term. I'm going to let that be the driver for my technique. So my goal is to get everything to be in terms of sine. Now how I'm going to do that is I will use an identity. There is an identity that relates sine squared and cosine squared. It's the Pythagorean identity, and it says cosine squared theta plus the sine squared of theta equals 1. I want to get everything in terms of sine, so I'm going to solve this for cosine and get cosine squared theta is 1, subtract sine squared theta. I am going to substitute this in place of the cosine squared. So now I have 1 subtract sine squared theta, subtract sine squared theta, plus sine of theta equals 0. Go ahead and combine my like terms and write it in descending degree. So -2 sine squared theta plus the sine of theta plus 1 equals 0. In this case, I want you to think -2z squared plus z plus 1 equals 0. Something like that, I would probably want to multiply both sides by -1 to get 2z squared minus z minus 1 equals 0. And then I would want to factor. And you can either use the AC method or guess and check. And I think guess and check is pretty efficient here because this leading coefficient is prime. as is the constant term. So the only possible way to factor, if it is in fact factorable, is to have a 2z and a z. And the only way to get a 1 at the end is a 1 and a 1. I'll figure out the signs by foiling it out. So I get 2z squared plus 2z plus z plus 1. And actually, I don't know if these are pluses or minuses, so I'll leave them off for now. I want it to be a minus 2z plus z and a minus 1. So in order to get a minus 2z, I put it as a, so that the 2z times the minus 1 gives me the negative. So 2z plus 1, z minus 1. How that relates to what I'm doing over here is I'm doing the same thing with signs. So I am going to also multiply both sides by negative 1 to flip things around. So I have a positive leading coefficient, and then I'm going to have 2 sine of theta plus 1, and then sine of theta minus 1 equals 0. You're just thinking about z being the sine of theta, and you're factoring in terms of something you've seen before, but now we're doing it with trigonometry. Then I apply the zero product principle, which says 2 sine of theta plus 1 equals 0, or sine of theta minus 1 equals 0. This first one says the same thing as sine of theta is negative 1/2, and this one is the same as sine of theta equals positive 1. So sine of theta equals negative 1/2, we've seen that before. In fact, we've seen it in this very set of notes. So here's the line y equals negative 1/2, intersects at 2 places, 7 pi over 6 and 11 pi over 6. And then y equals negative 1 is right here, and that intersects at 1 place. So my general solution, if I were to write that, would be the set of theta such that theta equals 7 pi over 6 plus 2 pi k, 3 pi over 2 plus 2 pi k, and then 11 pi over 6 plus 2 pi k. And that would be my entire general solution. So the main strategy for our quadratic trig functions is to just use what you know about regular quadratics, so factoring in zero product principle or the square root property, and then solve like we have been previously in the notes, finding all the angles that are solutions. If there's no specific instructions, you probably should provide general solutions. The only case I didn't do that on was right here on example A, and I specifically said I'm only giving the answers in 0 to 2 pi. This would have been a rather long general solution set to write, which is why I did that. So I'll freely admit that I was being lazy when I did that. But in general, provide that full solution where you're adding multiples of the period on to the end. So that is quadratic trig functions.